All right. Good evening, everyone. This is Astronomy 10, the online section, and I'm Celso Batalha, and you are who you are. And today we are in chapter 2, and I would like to browse through the course quickly. And for that, I would like to share my screen with you. And you should be able to see my screen now. Now I have Crystal there too. Welcome, everyone. Um, So today on Monday, we have discussions closed and homework too. The discussion, which was very simple, just an introduction of yourself to the rest of the class, who you are and what are your preferences. And I found several of you have hobbies, and one of the common hobbies is hiking, which is great, and the other one is for pictures, photography. Um, and I would invite you to go to the observatory this coming Friday. We have a public viewing and spend some time there, especially with Rick Francisco, which is here in the presentation. Rick is pretty much managing the observatory, and you can email him, excuse me, him directly if you want to have more information of what we do at the observatory. Um, I received a few pictures of the moon eclipse, and I thought about creating a display all the way to the end of semester, and you just go there and upload your picture if you have taken the picture of some astronomical object during this time from now to the end of semester, explaining what type of instrument you use, what kind of technique it was, if you did stack or not, and then let's make some sort of a competition for extra credits to see which picture is the coolest one. Um, so I will create this display during the weekend, and I thought that's gonna be cool. That's gonna be interesting. At least for some of you who like to take pictures, why not extend this hobby to the sky objects and change the camera a little bit, the inclination angle, and get something in the sky. Today's Monday, February 5th. So the discussion, Who Am I, is closing. So at midnight, if you haven't done, most of you have done. So there are a few of you not completed yet, and I mailed them. Um, the cultural background, this is for February 20. Usually, I will not read the discussions of a week that is supposed to close, more than 8 days in advance, because I don't have time. So what I will do is always read and comment on discussions that are going to close within 7 days, so that we all work together as a group. And if you want to do, discussions way in advance, you can, but I will not read them right now. So the next major group discussion that is going to come is the one closing on February 20. So once, beginning tomorrow, I will start reading this group discussion because there is no other one closing next Monday. And the reason why I extended this, my cultural background, because it's a long one. You have to do some research, and you have to invest some time reading and perhaps going to a couple of different websites, collect information, and share that with the rest of the class. Um, the idea is to have us doing a little bit of ethnoastronomy or archaeoastronomy, and go back in the past and try to identify the some of the astronomical causes of myth, religion, belief system, stories, allegories, um, and so it will demand just something much more in depth than the first discussion, which was just, hey, this is who I am, and I am very happy to be here and see you tomorrow. So, so that is the next group discussion. But we also have a one-on-one discussion that is closing tonight, and that is the one that has to do with. Oh no, I extended. Homework has been extended to February 12. So chapter 1 and 2, both of them are going to be closed next Monday. So you still have some time to complete if you haven't done so. But the discussion on Stellarium, where is it? There you go. Install Stellarium. This discussion is also closed tonight. And I had probably 5 students who joined the group, the class on Friday. I'm not sure if they have completed it yet or had time yet to do that. I will be using Stellarium throughout the semester, so you have to be able to use the software and upload solutions so I can make the grading part. So do not send response to my email because I will not be able to read it and I will not be able to grade it. It doesn't work. So make sure you do all your upgrading and answers. You all place them in Canvas, up in Canvas. So the Stellarium software is closing tonight. Also, if you haven't done yet, just go for. But I might be flexible since it's the first week of class or 2 weeks of class. I'm flexible to extend it in case you haven't done yet. Okay. And there is an extra credit, but the extra credit I'm not putting a lot of emphasis. If you do, that's great. If you don't do, that's great too. Extra credit in general, they are closing on Fridays, right? Not on Monday. So close on Friday. So this extra credit on dark energy is going to be closing this coming Friday. And then there is another on and on and on. And this Friday too, since we have the observatory, I would like to invite you to go there. We have one mandatory visit to the observatory. And perhaps if you could do your visit now, you're done. And then you have complete that assessment, that part of your grade. Okay. Do you have any question you would like to ask before we start? Nope.
I would actually.
Yeah.
Good evening. For the viewing at the observatory, is there a specific time to arrive?
Rick, this coming Friday is what, 7:30?
Yes, 7:30.
Yeah. Yeah, 7:30. And expect to stay there for about 1 hour because you have to go to a telescope. You have to identify what type of eyepieces we are using, type of telescope, if it's a reflector or refractor. And you have a list of sky objects you have to observe. And then you have to send me a report through Canvas. But I will upload a handout that you have to print it and take it and take it with you to the observatory. I will not have copies there. And before you leave the observatory, you have to give that handout to me with partially completed assignments. And there is a report, general report, that you have to upload in Canvas. But that you can do in about 1 week or so. Okay. But expect to stay there 1 hour. I think no more than 1 hour.
Okay. I know I personally happen to have work in the evening. Would there be a sort of, I guess, upper limit as far as when I could arrive at the observatory?
Go ahead, Rick.
We usually start shutting down around 10:15, 10:30.
Yeah. Oh, okay.
So you have time.
I mean, sometimes if I know someone's going to be coming up there, I will try to keep one of the observatories open.
You also have to, if you want to go there, not necessarily just to complete the assignment, but if you want to spend time, you want to really sit in and just take your time, I would recommend not to go there 7:30 because usually everybody arrives there 7:30 and you have lines and usually the kids are there. And we love kids, but they run around and they want to see and they want to see it again and they want to see again and again. So if you go at 9 o'clock, if you prefer, then it's much more relaxed, much less people. You can take a telescope or talk to one of us, and then you can train yourself how to operate and handle the telescope to find simple things, and then spend an enjoyable time and might learn something and might get excited about observing astronomy. We have adapters that you can play around installing your camera so you can take some pictures. It's not the ideal technology, but it's something. So if you have the time and if you have the inclination, that's what you could do.
Oh, interesting. And would those adapters work with any type of camera or digital SLR specifically?
The ones that Professor Celso is talking about is we have ones that you could use a smartphone that you could attach to the telescope, viewing through the eyepiece, and like if you could take images of the moon is probably one of the best things to take of. I'm not sure what time the moon is rising on that night. It's probably pretty late because we're already past. I think we're going into the waning third quarter, or last quarter.
Last quarter, yeah.
Yeah. So the moon won't rise till really late at night, probably around 11 or 12.
Yeah, midnight. We won't be there. I will not be there. Rick, I don't know. Rick can stay there at 4 in the morning. Everything's okay, great. I can take more. I can take pictures
when the lunar eclipse happens.
All right. So as I mentioned to you, I would like to go over some simulations that illustrate some of the sky motions we most directly perceive in the night sky. And there are 3 of them in particular. One is the so-called daily or diurnal motion, which is caused by Earth spinning on its axis of rotation. So if you imagine Earth like an apple, and imagine that apple with a stick that goes through the top, the stem part, all the way down, and you have the apple spinning around that stick. So that is pretty much Earth spinning around its axis of rotation. So that is the so-called daily or diurnal motion. That's the first basic motion I would like to call today, and this motion causes us, especially if you are observant and if you keep track of stars in respect to your horizon, to some dividing line connecting the sky and the mountains. So if you keep track of the stars where they are as the night goes by, you understand they are not in the same spot all the time. They keep changing in such a subtle way that you need to keep track of positions and then observe again or look at again in about 1 hour and then another hour, and then you see them kind of slowly drifting in the sky from the eastern part of the sky to the western part of the sky. So this first motion, as we learn in chapter 2, is caused because Earth itself is spinning in the space from the western part of the sky to the eastern part of the sky, the other way around. So if you imagine stars are so far away that we can't detect their motions unless we use technology like spectroscopy and other ones, which we are going to learn. So if the stars are so far away, and if we detect motions of these stars from the eastern sky to the western sky is because we ourselves are moving from the western part of the sky to the eastern part of the sky. That's the date of diurnal motion, and I hope to show with the simulation. So the next one, and that takes about 24 hours. So the next motion is the so-called Earth revolution around the sun that takes 1 year to complete the entire turn, and that is the difference between rotation, Earth rotation, and Earth revolution. Revolution is when the spin is done around an axis that doesn't go straight through the body of the object you're considering. So Earth revolves around a stick, if you think, that goes through the sun and not around Earth itself. That is the revolution of Earth. And there is a third motion that is very subtle. It's called precession. And precession is caused by a force, gravity force, that acts combining the gravity force of both sun and moon acts by kind of a bulging Earth equatorial region, and this combined pull forces Earth axis of rotation to wobble in space in a time scale of over 25,000 years. And that is very difficult to detect. And we found about precession once we could and when I say we, is astronomers in the past were able to accumulate data over several generations and compare data and realize there was some drift going on in the sky, a global drift we call precession. So let's start with the first one is Earth diurnal motion, which is Earth rotation on its axis. And let me take you guys out of here for now. So this software, Starry Night software, is not so much different from Stellarium. I'm a little bit more familiar with it, so I'm using instead of Stellarium, but you can do the same thing with Stellarium. So this is February 5th, 2018, 7:20, that's our local time. And the way it goes here, if you observe here, the time is ticking 1 second every second. And then if you look at the sky, this is pretty much the southern part. We are facing south. So eastern sky is to our left hand side, whereas the western sky is to the right hand side, right? So I'm going to call a line that is called the ecliptic. And the ecliptic line, as we learn in chapter 2, is a line where the sun locates itself throughout the year. So throughout the year, the sun is always located in this line called ecliptic. And ecliptic is also the name of Earth rotational or revolutional plane around the sun. As the Earth goes around the sun, it defines a plane, and the name of that plane is ecliptic plane. So again, the time is ticking, and we don't see anything happening. Orion seems to be there, and Betelgeuse, look at Betelgeuse is still there, right? Sirius, that's the star in the Stellarium assignment that I asked you to do by February 15, is still there, right? So it doesn't move. But look at what I'm going to do. I'm going to take Sirius. I'm going to center. I'm going to try to go and put it Sirius in the view of a telescope, if I could. It's so bright. I still don't see anything. But what if I change the time ticking? And instead of being 1 second every second, how about 30 times that? So every second, the time is going to be speeding up at a rate 30 times faster. So as you can see, look at that. The time is really going fast, and there is some satellite there. So you see there's satellites going down. By the way, this is a simulation. So the time is going fast. Can you see slowly the sky drifting? What if I increase this time to 300 times? So now the time is going faster. So it's already 8:20. And the stars, as we look south, the stars slowly rise in the eastern sky. Another satellite passed by, another one. And then they reach maximum height, which is the angle they make with respect to horizon due south. And then they start slowly setting in the western sky. So if we look closely, and more so if we increase the time, the speed in which this sky changes. My ecliptic line went down. Look at your moon there, Rick. Now the day is coming, the sun is rising, the moon is setting, and later on the sun is going to be setting too. And then we're going to go to tomorrow night. So we could think that the entire sky consists of an imaginary celestial sphere with stars on it, right? And let me just hide daylight. Now I'm hiding daylight. So the sun is seen against the stars in the background. So if we just stop for a while and think, okay, the stars are something in the celestial sphere, and celestial sphere is orbiting or going around us, we in the center of the universe, from the eastern sky to the western sky. This is pretty much the worldview called geocentric, Earth in the center, and we attempted to explain what we observed, what astronomers and philosophers observed 1,000 or 2,000 years ago, as if we were in the center of the universe and the whole universe would be orbiting Earth, which is not the true statement. So the reality is Earth, these mountains over here, this floor, are the one rising up from the western sky all the way to the eastern sky. I had an interesting visit with friends in Colorado, and it was a bunch of friends, different religion. They all like to see the sunrise, and then we went to the top of one of these mountains. That was a big hike, but we got on the very top, and I don't remember what time it was, but we want to see the sun rising, and so in the very far side we had a chain of not a mountains, it's a granitic mountain, and then 30 minutes or so before the sun appeared, so we have the glare of twilight. So the sun is pretty much coming up. We couldn't see the glare, and we just keep observing and looking and looking and looking, and then you have people praying, some people were dancing, doing all kind of things. It's a very eclectic and diverse group of people, and then suddenly the sun tipped in through the mountains. It's a beautiful view. And then for a while, I became an astronomer instead of being just somebody appreciating the sunrise. And then as an astronomer, I thought, okay, it's not the sun rising. The sun is not rising. The sun is not going up above the mountain. We are the one who are going down, revealing the sun. So just by this simple thought, it was filled with a sense of beauty and energy, because the energy to rotate the entire planet is magnificent. And when you stop and include physics and astronomy and knowledge in things you observe, um, they become a little bit more than just, a sun rising, right? Or perhaps dancing would be fine too. I'm just saying it's a different way to appreciate phenomena, natural phenomena. Okay, so let me freeze the time now. And let me show the same thing from a different perspective. This perspective. So this software is the Nebraska Astronomy Applets. There are several of them, and most of them are in our Canvas course. One of the modules that I put a lot of simulation there, it's there for your perusal. So what's going on here? There is a celestial sphere, and again, celestial sphere does not exist. You have this axis that goes through Earth, and if you extend this axis all the way to infinity, you define the north celestial pole, south celestial pole down here, and the equator, the celestial equator. So here's a point. Let me bring that point if I could. Don't know if I can change. Let me see. There you go. So if I started, let me put it in 37 degrees. That is San Jose, and that little dot should be in San Jose. If I go 118, I think.
No, 121.
Thank you. There you go. Are you sure? We should be in Pacific Ocean there. Huh? Okay, so here's San Jose right there, right? United States. And this is a dude that's pretty much us. North, which is behind the observatory. We are facing south, the campus, the parking lot. Eastern sky is the mountains or the hills in our left-hand side. And you have Highway 101 in the western part of the sky. And we are facing south. So if we start animation, so from the north perspective, we see Earth rotating from in a counterclockwise direction. And this counterclockwise direction in which Earth rotates, as we look down on the solar system from the north perspective, is the common direction of not only revolution around the sun, but also the common direction in which most of the planets spin around their axis. Exceptions, Venus, Uranus, because of collisions in the beginning of the solar system. We're going to go through that subject. But that is the counterclockwise direction. Now, because of that, if I start adding stars, so I'm adding some stars like, let's say, Big Dipper. Big Dipper is right there. Put a Big Dipper there, right? Big Dipper is there. It's not moving for all that, all from our little vantage point. So far away, the stars are so far away, we do not see they're moving with our unaided eye unless you use technology, and then you can measure 30 kilometers per second or so their intrinsic speed. But from our daily or hourly perspective, stars are rising in the eastern sky and they are set in the western sky. So I keep just adding more. Let's put in the Orion constellation. And you are seeing now the Orion constellation rising. And you see that dot now. We'll stop seeing Orion pretty soon. It's right here. See, it's not seeing anymore because Orion went down. So this rotating sky explains what we call daily or diurnal motion. Is Earth's rotation on its spin gives rise to this notion of daily or hourly progress of stars and planets in the sky. Would you like to comment anything here? Okay. So the second type of motion is the so-called Earth revolution around the sun. And for that, let's take a different perspective. So this is a perspective of the sun, and you have the inner planets, the terrestrial planets, called terrestrial because they are rocket type. We are going to learn in a few chapters in advance why these inner planets happen to be rocket type with the silica, a lot of iron. There is not a lot of volatile in this type of planets. Why is that? And we also see a host of little junk called asteroids that lie between the orbit of Mars and orbit of Jupiter that doesn't appear in here. But if you could to make an abstraction from your using a little bit of abstraction, so you could maybe think of all these different planets and this group of asteroids as being form or crystallization of material that happen to be in a circumstellar disk orbiting the sun itself. And let me show you briefly what I mean by that. EX Lupi is a star information, and astronomers did a nice video because it was found some crystal called olivine in the star, in the disk of the star, and I would like to show you what I mean by that. See, and when the stars are formed, a circumstellar disk is formed around the star itself, and out of this disk, I don't know why it's all green now. Yeah, out of this disk material, then dust, ice, little grains will start sticking together and grow in size, and eventually we have a system with a central star and a bunch of planets, asteroids, comets, all going around. So this simulation is just to show how this circumstellar disk around the star sets itself as the birthplace of planets, satellites, asteroids, and so on, and so on, and so on. And then you can see the final result in the simulation of our solar system, the sun in the very center, the 4 terrestrial planets going around, and I could even bring the outer planets. So here's the sun. There is a sun and the Jovian planets, the giant gas planets.
Ladies and gentlemen, no matter how strange things get here, they just get stranger.
Is that me?
There is a national monument in Wyoming.
Oh God, sorry
known
about
as
that. That was scary, you know. The aliens are attacking our cores. So where's the starry night? There you go. So now again, we are looking down on the solar system from the north perspective. The sun is somewhat immovable in the center of our solar system, and the giant planets going around in a counterclockwise direction, which is the same direction as the terrestrial planets go. And then we can zoom out, and then eventually we pretty much have explored our solar system. So what happened when Earth goes around the sun as it does? We ended up seeing different part of the skies throughout the year. Go back there. Oh, there you go. Chapter 2. If you double click that label, will open in a different window. It's easier to navigate that way. Although it's taking some time. That's our celestial sphere we saw, and that is the final result of Earth rotation on its axis of rotation. And if you go to different parts of Earth, you're going to see things behave in a different way. That is the geocentric worldview. And we have a discussion on precession and a discussion on astrology and astronomy that's going to come through. And Copernicus with his heliocentric worldview. Later, Kepler came and showed the orbits are not circular orbits like Copernicus have suggested, but they are elliptical orbits. And by doing so, it matched observations and theory quite well, which even Copernicus couldn't do it. But if we go back to the starry night, and back to our local time. Here's what I'm gonna do. I'm gonna change now. This is February 5th, 7:44 p.m. Let's put 8 p.m. right? Let me bring the constellations, boundaries, and let me bring the constellations labels so we know who they are. The constellations of the zodiac are here displayed. Let me bring the ecliptic now. The eclipse should pass through the zodiac right there. And what I'm gonna do, I'm gonna advance 1 month at a time, right? So February 5th, 2018, 8 p.m. And what I'm gonna do, I'm gonna go how about a lunar month? Yeah, days. Just advance sidereal month. So Gemini is right here in respect to our horizon is somewhere between southeast and south. That's Gemini right there. So 1 month later, well, I have to bring the time correct. March 5th, 2018, so 1 month later, Gemini is a little bit to the right, almost on top of South. So if we go February, March, April, now Gemini is more somewhere between South and Southwest, April, and then May. See what's happening too? At this time, as we approach summer, the twilight start coming in. You know, even at 8 p.m. it's still somewhat bright out there. Not good for our observatory. We have to start a little bit later. And then another month. And then Gemini, I can't even see it. So these, in fact, let me go 8 p.m. Oops. There you go. 8 p.m. June 5th. Sorry. So Gemini is all the way here. It's almost setting. Look at that. So which means because of this Earth revolution around the sun, as we saw in the previous simulation with the sun in the center and Earth going around, as we look in a certain part of the celestial sphere at a certain time, the constellation seems to be drifting westward, right? So every month the constellations are a little bit westward. Why is that? Because in addition of us spinning in the space from west to east, we also go around the sun from the western part of the sky to the eastern part of the sky in a prograde motion, in a counterclockwise direction as we look down from North Celestial Pole. And because of that, the constellation seems to be drifting always on and on and on towards west, right?
Yes, please.
Yes.
Oh, sorry.
Yes, somebody said something?
Oh, yeah, I did. I forgot the mic was on. Sorry about that.
Oh, no problem. So if I just do another type of exercise, let me move this down. And sidereal day. And what I'm gonna do, I'm gonna be getting rid of daytime. If I can, wait a second. There you go. Daylight is gone. I still have the constellations. Leo is right here. See Leo right there? Looks like the lion mane with Regulus right there and the lion tail. I can perhaps bring the illustration of a lion right there. See that? So the lion or Leo is in the very middle part of the sky. So let's imagine that we are facing Leo all the time. As Earth goes around the sun, we keep facing Leo all the time. And look what happened. See that little thing drifting from west to east? See the moon coming by? See the sun coming by? Who are these fellows? They are planets. So if you manage to stare at a given sky region, always, right? Imagine you get out of space, you take a spaceship, and then you keep staring at the same part of the celestial sphere, you can see, I think we almost got an eclipse there. Look at that. Was not an eclipse. So what you see is most of the planets, certainly the moon and the sun, are always drifting from west to east in respect of the background stars. And this type of motion is called prograde motion. Prograde or direct motion, which is the normal motion of planets and the sun and the moon. But look what happened with Mercury. Can you see Mercury now is retrograding? Is going backwards in respect to its normal direction. And if I speed up the process, see Venus retrograding, and Venus will start prograding again. The moon always progrades. Every time the moon passes by is another month. And now Mars is prograding, and Mars will start retrograding. Oh, Mercury is retrograding. So why this progression and retrogression occurs, see the comment, is because we are staring exactly we are on Earth, and we are staring at same region in the sky always, like Leo, as we were. And sometimes we pass Mars, and then we see Mars retrograding. And then if we keep looking at Mars, now Mars seems to prograde in respect to where you are. And then eventually we will see Mars retrograding again. So progression and retrogression are kind of motions in the sky that help astronomers to create this worldview, different worldviews that we are studying in chapter 2, which is the geocentric and the heliocentric worldview. They had to explain progression and retrogression in their worldview. The first worldview that came by with Aristotle was Earth in the center of the universe, with planets going around, Earth in a circular path, because circle was a perfect curve. It's supposed to be a magical curve, a symbol of harmony that they thought existed in the skies. And now we know skies are full of collisions and interaction, galaxies merging and cannibalism, all kind of things. But they thought everything was perfect out there. Only Earth was subject to decay and destruction, right? People die, people battle, you look in the mirror every day, you have another wrinkle coming in. It's decaying, but distractions also exist in the sky, except in a longer time scale. The geological time scale, if you will, if you want to, astronomical time scale, and things take long time for the changes to be perceived. So that is the second type of motion, Earth revolution around the sun. And let me end with the third one, which is precession. So precession, I don't have a good simulation here. The book might take you on a better simulation, but what I would like to show here is the effect of precession. For instance, I was born in July 31st, and friends of mine, they are astrologers, they tell me that I'm a Leo, right? And then if I'm curious, I go to July 31st. Oops, July and 31st. There you go. That's when I was born, and this time of the, and then, but I was in Rio, but it doesn't matter. So let me take the sun's position. Where's the sun? Where's the sun over there? See the sun over there, July 31st, and then I'm curious, right? And let's say there is an eclipse, I can get rid of the glare of the sun, never look straight at the sun. And then I'm going to bring my labels.
No.
What is it? Oh, a view. Let's bring boundaries. Let me bring the names too. And then for my surprise, the sun is not in Leo. Where is Leo? Leo is right there. The sun is in Cancer. For instance, who knows the astrological sign? Wilfred, do you know your astrological sign?
My astrological sign is Cancer.
Cancer. When were you born?
July 15th of 91.
July 15. July 15. July 15, the sun was in Gemini. Why is that? Now, as you can see here, July 15, 1953. I mean, which year that was? Are you younger than me?
No, yes, 1991.
Okay, even 1991 is the same position. It's in Gemini. But if you go BCE, in July 15, at about 1000, the sun was in Leo. Which sign you said you were?
Cancer.
Cancer. Really? Yeah, even in those days it didn't match it. So precession does this trick, right? And most of the astrological sign and most of the nice signs as people carry nowadays was established somewhere around this time, 1000 BC or 2000 BC. And we have an assignment that I help you to find where the sun was when you were born. And then the point of the assignment is to make this discussion. Why we think astrology works or not. Because the sun, sometimes it's not in the region that we thought it should be. But why the sun has shifted all this time is because of precession. The Earth axis of rotation right now points towards Polaris, but thousands of years ago was pointing in a different direction because the axis of rotation wobbles in the space as a result of this combined gravitational pull of the sun and moon on Earth, and then this wobbly leads to what is the so-called precession of equinox. on March 21st, when the sun crosses the celestial equator going northward, and we call that moment, this astronomical moment, the beginning of spring, March 21st. So right now it's not in March 21st. It is, in fact, we said that to be in March 21st, but 2,000 years ago, the sun was seen against Aries. Now it is against a different constellation, Pisces or so. So that is the third one. It doesn't affect us much. Naturally, the date or diurnal motion, because of days and nights, is the type of motion that really affect us directly. And Earth revolution around the sun gives rise to seasons, which is very important to us too. And precession, not a lot of changes on Earth. Okay. So still to cover chapter 2, I would like to have a video on moon's phase. And I will prepare, and I will let you know when I'm preparing that. If you could jump in, that would be good, but it's not going to be on Monday, because next week, in fact, I could do next week, but you are working on the subject now, and I think I should step in and prepare a video on moon's phase. Moon phase is cool. Moon is one of the conspicuous objects in the sky. And I would love if you can learn how identify phases in the sky as you see, and also predict at what time of the day these phases are supposed to be in. Okay, and there's a little trick you can do, but it's very helpful. Okay. All right. Any point? Any discussion? Sorry, I stay talking all the time, but I want to run the simulation and show where to find it. And you can, Ricky, did you play with precession with the Stellarium?
Not with Stellarium. Yeah, Stellarium I did.
You did. So it works. It goes back and changes the constellations.
Yeah.
Okay. So they improved.
You can go back 10,000 years.
And the constellations change in the sky.
Yes.
Okay. All right.
When I found when my birthday, my sign was, it was like in 5,000 years ago.
All right.
When the stars lined up with the sun.
Okay. Sounds good. All right, folks. I will start taping this and it should be available tomorrow. Good night.
Great. Thank you. Good night.
Thank you. Thank you for coming. It's great. Hey, Trisha, you were there. I didn't know. No, I can see your name there.
I've been here.
So I didn't see you. So it's a repetition. Let me stop taping for a second.